everyone, and welcome to some more remote learning. Today we're going to go over Calculus 2. We're actually finally going to talk about the Taylor series, but mostly on this worksheet, I'm going to be going over the Maclaurin series, which is a specific subset of Taylor series. So let's jump in. Now, Taylor series are very similar to those Taylor polynomials, which we talked about a couple videos ago. But remember, Taylor polynomials went from some starting index to an ending index of, let's say, n, some variable n. Whereas Taylor series, that upper index goes to infinity. So if we suppose the function f has derivatives of all orders on an interval centered at the point a, the Taylor series for f centered at a is, well, think back to those Taylor polynomials. Let's write out a couple of terms. We have f of a at the start. Then we're going to add that to the first derivative of a, multiplied by x minus a to that first power. And then we're going to add that to f double prime of a. So the second derivative at a over 2 factorial. That gets multiplied by x minus a squared. Then, let's go another term. We have the third derivative at a over 3 factorial times x minus a cubed, continuing to sum all of those up, going towards no longer an n value, but going towards infinity. Writing that in sigma notation, that's going to be the summation from k equals 0 to infinity of the kth derivative of a all over k factorial times x minus a to the k. That's our Taylor series, the kth derivative at a over k factorial times x minus a to the k, summing all of those terms from 0 to infinity, our Taylor series. Now, a specific type of Taylor series centered at an a value of 0 is called a Maclaurin series, and this has the form of, well, if you think about plugging in zeros everywhere for a, especially when we're plugging in x minus a, x minus 0 is just going to be x. So the Maclaurin series has the form of the summation from k equals 0 to infinity of our kth derivative at no longer a, because remember, we're specifying that a is 0. So the kth derivative at 0 all over k factorial times x, and that minus a is no longer necessary because subtracting 0 does nothing to the value of x. So that will be x to the k. Now, if you remember, we're still in the section on power series. And power series is some summation going towards infinity of c sub k times x minus a to the k. Note that the Taylor series and Maclaurin series are both also technically power series. So our c sub k, if we were talking about that power series general form, in the instance of the Taylor series, is the kth derivative of a all over k factorial. That is our c sub k. And our c sub k for the Maclaurin series is just that c sub k of the Taylor series, manipulated just slightly. We're taking the kth derivative now, but we know what a is. So the kth derivative of 0 all over k factorial. So the first time I learned about power series, Taylor series, Maclaurin series, it all kind of melded together. And it wasn't until I started tutoring that I got a great visual in my head. And hopefully I can clarify that in less than a minute in this quick little diagram. If we start, this whole section is all about power series. And power series have that general form of our c sub k times x minus a to the k. We can all agree on that. But if I'm specifying that c sub k is this, Taylor series is that subset of power series. Yeah, I have other types of power series that I can branch off to, but the branch I'm looking at is this Taylor series branch. And Taylor series, if we even define that a value, goes even further into a subset. That is the Maclaurin series. So a Taylor series is a type of power series, and a Maclaurin series is a type of Taylor series. but that still means that Maclaurin is a power series. But a Taylor series does not necessarily have to be a Maclaurin series. For example, if I centered it at an A value of 1, then we no longer have a Maclaurin series. That's just the Taylor series centered at a specific value other than 0, which isn't a Maclaurin series. And just as a Taylor series doesn't have to be a Maclaurin series, a power series doesn't have to be a Taylor series, which we had plenty of examples of those when we were practicing finding those intervals of convergence. But hopefully that clears up any information and helps you understand the difference between power, Taylor, and Maclaurin series. But for now, let's continue on and actually jump into this example. Now, example 1 says that we're going to be finding the Maclaurin series for f of x, which I'm defining f of x as 1 over 1 minus x. And then I'm going to determine that interval of convergence. Right away, this is a fairly easy problem because, let me give you a little hint, what if I wrote this? A over 1 minus r. This should be super familiar. Right now there should be red flares going off. A over 1 minus r? That's what a geometric series converges to, if that r value is between -1 and 1. So from this function f of x, my a value is 1, my r value is actually x, which means if I'm converging, r has to be between -1 and 1, and r is x, so that means I'm going to converge when x is between -1 and 1. And let's go ahead and write this. The summation from, we're geometric, so that's k equals 0 to infinity of a r to the k. Our a value is 1, so I'm not going to include that. Our r is x, and that's raised to the k. A r to the k. So this f of x is the summation from k equals 0 to infinity of x to the k, as long as x is between -1 and 1, because that's the interval for which it converges on, because this is a geometric series. So no time at all to get this answer. But let's actually use what we just practiced. Let's write out this Maclaurin series. It says that we're finding the Maclaurin series. Right away, what does that mean? That we're using that Taylor series, but it's centered at 0. That's our Maclaurin series. Let's quickly write out our form for a Taylor series. So we have f of a plus f prime of a times x minus a to the first, plus f double prime of a over 2 factorial times x minus a squared, plus f triple prime, so the third derivative at a, over 3 factorial times x minus a cubed, and so on. Now remember, this is a Maclaurin series, so I care about when I'm plugging in a of 0. So I want f of 0 plus f prime of 0 times, well, x minus 0 is just x, and then I'll add that to f double prime of 0 over 2 factorial times x minus 0, which is just x, squared, plus f triple prime at 0, all over 3 factorial times x minus 0, which again is just x cubed. Oh, and sorry about that glare. I just fixed it, so hopefully it works out. Thankfully it wasn't on the work or anything, so. All right, and then we're just going to continue that pattern on. So you can see that Maclaurin series almost simplifies that Taylor series down. It's a little bit less writing, which is nice. Now in order to fill this out though, I think a table is going to come in pretty handy here. So I care about my kth derivative of x, but really what I care about is when it's at 0. So I like doing a table just because it helps me fill this information in a little bit easier. So if I'm just looking at, I'm not taking the derivative, just my original function. That is 1 over 1 minus x, which I'll go ahead and write as 1 minus x to the -1. Plugging in an a value of 0 for x, we get 1 minus 0, which is 1. 1 to the -1 is 1, because that's like 1 over 1. taking the derivative, we get negative 1 minus x to the negative 2. You see how I brought that negative 1 down in front, but remember the chain rule. We also have to multiply by the derivative of the inside, which is going to be multiplying by a negative 1, because the derivative of subtracting x is going to be a negative 1. Negative times negative, positive. 1 minus 0 is 1 to the negative 2. So again, we get a positive 1. Now, taking the derivative again, remember this was a positive, so let me go ahead and erase this negative 1 and this negative. It was a positive 1 minus x to the negative 2. So I'll drop that negative 2 down in front, and we'll get 1 minus x to the negative third, but again, multiplying by that negative 1. So you can see a negative times negative is a positive. So this will be 2 times 1 minus x to the negative 3. 1 minus 0 to the negative 3 is a positive 1. 2 times 1 is a positive 2. And then lastly, let's take that third derivative. So dropping that negative 3 down, negative 3 times 2 is a negative 6 times 1 minus x to the negative 4, and that's all multiplied by a negative 1. So again, negative times negative, that's going to be a positive. And 6 times 1 minus 0 to the negative 4 is a positive 6. So filling this in, f of 0 is 1, plus f prime of 0 is 1, and we're going to multiply that by x, plus the second derivative at 0 is 2, and that's divided by 2 factorial, which is 2, and then we're multiplying that by x squared, plus the third derivative at 0 is 6, and that's divided by 3 factorial, which 3 factorial is 3 times 2 times 1, which is also 6, and then that's multiplied by x cubed, and so on. So I'm sure you guys are already picking up on that pattern and simplifying in your head. Let's go ahead and clear this out, and I'll go ahead and rewrite this really quickly just for neatness. So let's simplify. We get 1 plus 1 times x is x, plus 2 divided by 2 is 1, 1 times x squared, plus 6 divided by 6 is 1, 1 times x cubed, and so on. You can see that we do indeed get the summation from k equals 0 to infinity of x to the k. X to the 0, x to the first, plus x squared, plus x cubed, and so on. So our next step, it says to determine that interval of convergence. We already talked about the interval of convergence when it comes to the geometric series, so I won't go further into that, but I want you on your own to try either the Rooter ratio test, so feel free to pick one of those, find that interval of convergence, and for this one, don't forget to test your endpoints. So go ahead and try that on your own, and let me know what you get in the comments below. Now, example 2 is going to be a little different. Again, we're still finding the Maclaurin series for f of x, but this time our function is going to be sine of x, and then we're going to need to determine the interval of convergence for that series. Remember, looking back up at that formula if necessary, we have f of a, which if this is a Maclaurin series, what's our a value? For a Maclaurin series, that a value is 0. So we have f of 0 plus f prime of 0 times x minus 0, which is just x to the first, plus our second derivative at 0 over 2 factorial times x minus 0, x squared, plus that third derivative over 3 factorial times x cubed, and so on. Again, I like to think of this as a table. So I'm going to take my kth derivative of x, and then I'm actually going to plug in 0 for those x values. So not taking the derivative at first, we know that f of x is sine of x. And the sine of 0, either referring to our unit circle, the sine of 0 is 0. So our first term is 0. And then we're going to add that to, taking the derivative of sine is cosine of x. Cosine of 0, that's a positive 1. So now we have 1 times x. Now notice, taking the derivative of cosine is a negative sine of x. Plugging in an x value of 0, negative sine of 0 is just 0. So now we don't care about the 2 factorial or the x squared because that derivative 0 times anything, we're going to get 0 for this. Now let's do our third derivative. That's going to be negative sine goes to negative cosine of x. That'll be a negative 1. So now we're going to be adding negative 1 over 3 factorial times x cubed. Now, I'll be completely honest. Just from these two terms that aren't 0, it's going to be hard to really visualize that pattern. So what I recommend is doing at least 2 more derivatives because we know the derivative of negative cosine goes right on back to sine. So we're going right back up to the top. So again, we're going to be plugging in 0 for a k value of, well, this is k of 0, 1, 2, 3, for a k value of 4. And then this would be k equals 5. This would be k equals 6. This would be k equals 7, and so on. So my next term I know is going to be 0. So that gets rid of my x to the 4th. But now my x to the 5th is going to be a positive 1. So that's going to be plus 1 over, that'll be a 5 factorial by the time I'm to x to the 5th. So I'll multiply it. Then again, I'm adding 0 because when k equals 6, my derivative is back to 0. But when k equals 7, my derivative is back to being a negative 1. So I'm going to add negative 1 over, well, this is a k value of 7, so I'm at 7 factorial at this time, times x to the 7th, and so on. Because that derivative cycles back, sine, cosine, negative cosine, sine, cosine, negative cosine. We'll continue to get this pattern as we go. So I'm going to erase this, rewrite some stuff so that you can see that pattern. So the pattern we're going to do is I'm only going to take the non-zero terms. So my first non-zero term is 1 times x, which is just x. My next non-zero term is subtracted. So I'm going to subtract 1 over 3 factorial times x cubed. So I'll just write that as x cubed over 3 factorial. My next non-zero term is a positive. So I'll be adding that to 1 over 5 factorial times x to the 5th, or simply x to the 5th over 5 factorial. Then my next non-zero term goes back to being a negative. So then I'm going to be subtracting again that x to the 7th over 7 factorial, and so on. So from here, I think now we've got enough information to really pick up on this pattern. We're going to have the summation from k equals 0 to infinity. And then what I want to note is that if you're looking at each of my exponents, I'm only taking the odd ones into account. Same with those factorials. They're only the odd factorials. So if you can envision me putting a 1 with this x over 1 factorial, maybe the pattern becomes a little more clear. So I'm going to have some value x, and I'm going to raise it to, well, I want only my odd numbers. I know even numbers are multiplied by 2. So as opposed to doing 2k, which would pick up all my even terms, I want to do to the 2k plus 1. So you can see if I plugged in a k value of 0, 2 times 0 is 0, x to the first is x to the first. And then let's plug in a k value of 1, 2 times 1 is 2, 2 plus 1 gives me 3, x to the third, we've got that next term, and so on. But that second term's negative, and then the next term's positive, negative to positive, and so on. So I have to account for that oscillation. So I need to have some negative 1 raised to a power, and I'll go ahead and raise that to the k, because negative 1 to the 0 gives me a positive for my first term, negative 1 to the 1 gives me a negative, negative 1 squared gives me a positive, and so on. So now I have my x's taken care of, and whether they're positive or negative taken care of. Now I just got to concern myself with that denominator. Well, very similar to how we figured out those exponents, it's only the odd ones. So this is going to be 2k plus 1 factorial, because that'll get me 1 factorial when k is 0, 3 factorial when k is 1, 5 factorial when k is 2, and so on. So that's my Maclaurin series for the sine of x. Now the fun part is going to be figuring out that interval of convergence, because this isn't as simple as a geometric series, because it's not. So we're either going to have to do the root or ratio test. And because we have this factorial, let's do the ratio test. It's always a good sign to do the ratio when we have a factorial. So I'm going to take the limit as k approaches infinity of the absolute value of a sub k plus 1 over a sub k. If you need a refresher on the ratio test, I have a video on that. And if you need a quick little refresher on how to find the interval of convergence, I have a video as well on that. So I'm going to go through this without going into too much detail, but let's get started. I'm going to, as opposed to dividing by a sub k, I'll multiply by its reciprocal. So a sub k plus 1 is going to be negative 1 to the k plus 1, which this negative doesn't really matter because I know ultimately in the end, these absolute value signs are going to make what's inside of that positive. So I'll drop that off. So I'll have x to the 2 times k plus 1 all over 2 times k plus 1 factorial. And I'm going to be multiplying that by the reciprocal of a sub k. So 2k plus 1 factorial all over x to the 2k plus 1. Now simplifying this down, I'm going to get the limit as k approaches infinity of distributing this 2, I'll get x to the 2k plus 2 plus 1. So this would be x to the 2k plus 3, which doesn't help me out. I want to try to get x to the 2k plus 1. So I'm going to leave this as x to the 2k plus 1 plus 2, because that's the same thing as x to the 2k plus 3. But writing it like this allows me to split off in x squared. So getting rid of that plus 2, I'll have x to the 2k plus 1 times x squared. And that'll be all over 2k plus 3 factorial. Distributing that 2, I'll get 2k plus 2 plus 1, which is 2k plus 3 factorial. Now this factorial is bigger than the factorial in my numerator, so I'm going to write this until I get that numerator somewhere in that denominator. So 2k plus 3 times 2k plus 2 times 2k plus 1, there it is, times 2k plus 1 factorial. So finishing this out, I'll continue multiplying. So that numerator gets multiplied by 2k plus 1 factorial, and that denominator gets multiplied by x to the 2k plus 1. Now you can see that my 2k plus 1 factorial cancels out with 2k plus 1 factorial. My x to the 2k plus 1 cancels out with x to the 2k plus 1. So my limit as k approaches infinity is going to equal x squared all over 2k plus 3 times 2k plus 2. Think about as k approaches infinity. K is only in the denominator, so this fraction is going to continue to get smaller and smaller because the denominator is growing. So the limit is going to equal 0. Now this is really nice because what test did we do? We did the ratio test. And the ratio test says that whatever we get for that limit value, as long as it's less than 1, we're converging. And 0 is always less than 1. So our interval of convergence is all real numbers. X goes from negative infinity to positive infinity. Whatever we plug in for x doesn't matter. That limit's still going to be 0. So our interval of convergence for this series is negative infinity to infinity. Now I know this wasn't part of the question, but from here you should also be able to tell me the radius of convergence. But let's move on to our third example. In example 3, we're now going to start manipulating these Taylor series, or more specifically, manipulating these Maclaurin series, because both A and B are also centered at 0. So we're going to use our answers from example 1 and 2 to determine the Maclaurin series for the following functions. So this should be very similar to work we've already done in that previous video where we were just combining power series, because Maclaurin series are Taylor series and Taylor series are power series. So we can rewrite f of x as 2x cubed times 1 over 1 minus 8x. 1 over 1 minus 8x looks pretty close to 1 over 1 minus x. The only difference is that as opposed to plugging in x for everything to get x to the k, I'm going to be plugging in an 8x. So I should have 2x cubed times the summation from k equals 0 to infinity of 8x raised to the k. That's my series for 2x cubed over 1 minus 8x. Now, we can try to simplify this down by bringing that x inside our series and the 2 as well. Why not? So we'll have 2x cubed times 8x to the k, which if I want it to be written together, I'll distribute this k inside of here to both the 8 and the x. So this is going to be the summation from k equals 0 to infinity of 2, and now I'm going to bring that 8 to the k outside. So 2 times 8 to the k times x to the, well, combining x cubed with x to the k, since those are multiplied together, I will add those exponents, x to the k plus 3. And then lastly, f of x equals the cosine of x. Now this one isn't quite as simple as A, where we were able to just quickly rewrite a few things, plugging in a different input and then multiplying through. Cosine of x, if we're relating this to example 2, remember cosine of x is the derivative of sine of x. So if I'm writing this out, if I have the sine of x, what was that equal to? Well, that was x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on. Which finally, for our summation, we got the summation from k equals 0 to infinity of negative 1 to the k times x to the 2k plus 1 all over 2k plus 1 factorial. So rewriting cosine of x, writing that as that Maclaurin series or writing that as some power series is as simple as taking the derivative. So I'm going to try to keep this in line just so you can see it visually. If we have the cosine of x, that's the derivative of sine of x. The derivative of x is 1. The derivative of x cubed over 3 factorial is going to be 3x squared over 3 factorial. The derivative of x to the 5th is going to be 5x to the 4th over 5 factorial. Then x to the 7th over 7 factorial is going to be 7x to the 6th over 7 factorial, and so on. Now before I go ahead and differentiate this power series, let's find that pattern so that we can double check. I'm going to actually rewrite this now that we've taken the derivative, just to simplify it down a little bit more. This is 1 minus, notice that 3 over 3 factorial, 3 is the largest factor in 3 factorial, so we're going to be left with x squared over 2 factorial. And then again, 5 is the largest factor in 5 factorial, so this will be x to the 4th over 4 factorial. Can you guess what the next one is? That's going to be x to the 6th over 6 factorial. So you can see we have a very similar pattern, except as opposed to dealing with odd exponents, we're now dealing with those even exponents. Because 1, if you want to think of it, could be written as x to the 0 over 0 factorial. So based on our pattern, we'll easily get the summation from k equals 0 to infinity of, this is going to be x to the, we want the even ones now, so it'll be 2k Again, we're still oscillating between positives and negatives, so we still want negative 1 to the k here. And this time it's going to be over 2k factorial. So you can see that everywhere where there was originally a 2k plus 1, I turned it into a 2k so that I could get those even exponents as opposed to the odd ones. That's that power series representation of cosine of x. But if you didn't feel right like writing all of these terms out, take a look. We can just differentiate this series. And we're differentiating with respect to x. So how we do that is we drop the exponent down in front and we decrease that exponent value by 1. So this would be the summation from k equals 0 to infinity. We still have negative 1 to the k. I'm going to bring that 2k plus 1 down in front, multiply it by x to the 2k plus 1 minus 1, which is x to the 2k. And that's all over 2k plus 1 factorial. But wait a second, 2k plus 1 is the biggest factor in 2k plus 1 factorial. So I can rewrite 2k plus 1 factorial as 2k plus 1 times 2k factorial. That way you can see my 2k plus 1 gets canceled out to leave me with the summation from k equals 0 to infinity of negative 1 to the k times x to the 2k all over 2k factorial. The same thing we got here when we were just looking at the pattern. And again, that was all by noticing that the sine is the integral of cosine of x, or cosine of x is the derivative of sine, making that relationship and building that power series based on it. That's something that we did in the previous section and something we will continue to do with Taylor series and Maclaurin series, because what are both of those? They're both power series. So hopefully you found this video helpful and it cleared some things up for you. If you have any questions, please feel free to leave them in the comments below, and I or one of your peers will get back to you as soon as we can. So good luck with your Calc 2 work and see you next video.